Hey guys, we're going to do another one. This one's a little bit crazier. Okay, it's Unit 3, Handout 5. And looks like we're correcting to you 90% here on this particular one. And so we're going to just try to see if we can figure this out. Now this one's a little bit more complicated than most, okay guys, because we can use some information up here. 250 volt, 40 volt, 60 hertz, 5 horsepower motor. The efficiency is 85%. You know, what we have to do first here, guys, is try to figure out what's going on with this motor. And then once we figured out what's going on with this motor, we'll see if we can actually draw a power phasor diagram for this motor. So I'm going to draw this motor for a second here. There it is. I'm actually drawing the motor here. And that 5 horsepower that it's talking about there, guys, it is the motor at the shaft, okay? Because anytime you see the horsepower of a motor, that'll be the output of the motor. And so this is actually, power out, okay? Now, in order to figure out what's going on electrically here, what we need to try to figure out is power in. If we know power in, then we can start, with this question, basically. Okay, guys? So here's our output power. Now, there is an 85% efficiency problem here, okay? 85%. That means there's more power in than going out, and that's what's true with all motors, right? Because some of it's lost, there's heat and things like that. So how are we going to figure out the input power? Well, the first thing we're going to do is convert this to watts, okay? And there is 746 watts per horsepower, right, guys? So if I take my power out and calculate it in watts, it's going to be 5 times 746. Okay, and I'm going to do that right now for a second. 5 times 746. It's going to be 3730 watts. Okay, and then I can calculate my input power, because power in, guys, is going to be power out divided by the efficiency. And that's because of this formula that you learned in level 1. I'm going to use this as a piece of scrap paper, okay? The efficiency of any machine is equal to useful power obtained divided by total power used, okay? So the efficiency of anything is the output power over the total power that's consuming. And, if my furnace is 97% efficient, that means that 97% of the energy that's going in to the furnace is heating the house, and the other 3% is going out the chimney, basically. All right, and so it's useful power obtained over the total power used. Now if I transpose this formula, then power in is going to be power out divided by efficiency. Okay, and that's what I've got right here. And believe it or not, you learned that in level 1. All right, guys, so 3730 over 0.85, and this is going to get me my total power. So I got 3730 here divided by 0.85 equals 4388 watts. Okay, and so that just means that's my electrical energy in. This is my mechanical energy out. Okay, guys. And I want to make sure that my input power is more than my output power, because there's no machine on the planet that has a lower input power than output power. All right, that just doesn't exist. And I've seen students try that because they multiply this instead of divide. All right, so make sure you divide so that you get an input power that exceeds your output power. Some of the watts here, between here and here, between here and here, is being lost as heat, and that's what's going on here. 4388 being consumed by the motor, 3730 coming out at the shaft. The rest lost, okay, heat. All right, so now that we know that, we can do our uncorrected power phasor diagram, okay, guys? So I'm going to do that right here, and I know it's going to look like this. All right, and that's going to be there, that's going to be there, that's going to be there. And the question is now, where does this 4388 go? Does it go here, here, or here? Well, the big hint here is that this measured in watts, okay? And if it's measured in watts, it's true power. The other reason we know it's true power is because it's actually doing work, okay? That's mechanical horsepower. And true power is always heat or horsepower, all right? And, even the stuff that's being lost as heat, that's true power. We're not using it, but it's definitely heating something. So 4388 watts, okay? Now, our power factor is 0.7. Now that we know that, we should be able to calculate our VA and our VARs. Our VA will be our power divided by our power factor, okay? And that's because power factor is, P over VA, transpose it. So this is going to be 4388 divided by 0.7, okay? And, if I know my VA and my power factor, my power is going to be my VA times my power factor. If I know my power and I'm looking for my VA is going to be my power divided by my power factor, and that's just how that gets transposed. 4388 divided by 0.7. 6269, okay? 6269 volt amps. Last thing I'm going to calculate is my VARs. It's going to be 6269 squared, minus this. So I'm just going to calculate that, okay? Because I'm hoping by now that you guys got that figured out. 4388 squared equals root equals 474477 VARs. All right, guys? We're going to make sure that we're on the right track here. Yep. Okay, so that's our reactive power in this circuit, and this is uncorrected, right, guys? Now, if I'm going to correct this thing to 90%, then I have to draw a corrected power phasor diagram, and I'm going to do that right here. All right, now step 1, true power gets moved directly from here. Okay, step 2, my reactive power gets moved because this is VARs XL, and I got it. It's still there. Okay, so here's my VARs XL, 4477. Okay, VARs. Now, if I was correcting the unity, guys, my capacitor would just be 4477, right? But I'm not correcting the unity. I'm correcting the 90%, which means that my capacitor is going to take up some of this stuff. Okay, so this is going to be my cap. All right, and I'm going to leave some phase angle, all right, because I'm leaving 0.9 in here, and my VA will be here, and this would be my VARs X. Okay, that's going to be the reactive power in the circuit that I'm going to live with right there. And here's my cap, which I haven't figured out how long it is or what it is yet, but I will in a second. Okay, so now that we know that, I can calculate my VA, and then I'm going to calculate my VARs, and then I'm going to calculate my cap. All right, guys? So my VA, it should be 4388 divided by 0.9, which is the power factor after correction. Right, guys? So 4388 divided by 0.9. My VA after correction is going to be 48706 volt amps. All right, guys? And I'm going to be able to calculate my VARs X too. It's going to be that squared minus that squared, square root, right? So this squared minus 4388 squared equals root equals. Looks like I'm going to be living with 2125 VARs. Okay, and that is not your cap. Okay, the cap is actually going to be, well, it's that green line there. It's going to be the VARs in the circuit that I started with minus the VARs in a circuit that I'm going to live with. So my capacitor is going to be 4477 minus 2125. Oops, 25. Okay, and so I'm going to calculate that for a second here. 4477 minus 2125 equals. The cap is going to be 2352 VARs. Okay, and that is the answer for 8A. Okay, guys? Now, calculate the new value of line current. I is always equal to VA over E. Okay, and is the VA after correction 4876 over 240. 4876 divided by 240. 20 amps. Okay, guys, that's going to be my current after correction. All right, guys. I know I went pretty fast, and I hope you could keep up. And if you can't, slow the video down or pause it. All right, guys, and come back for the next one. Have a good one.